Welcome to Unit 15 and 16. We start integration in two variables. So the definition of the integral is exactly the same than we have done in single variable. It's more interesting because a region, we integrate now a function of two variables over a region, and that's more rich. And so what we do is the same thing we have done before. We just sum up over all grid points, k over n, l over n, and then we look at the function value at that point. We add up this function value and divide by 1 over n square. 1 over n square is the area of this, one of these base areas. We take this has an interpretation as a volume. That's the definition of the integral. Especially important is if the function f is equal to 1. There is a beautiful theorem of Fubinis, Italian mathematician, who has shown that if we have a rectangle, and that only works for rectangles, if you have a rectangle, then it doesn't matter which order we integrate, whether we first integrate with respect to the x variable or the y variable. And actually it also leads us to the method how to compute double integrals. We reduce them to single integrals. And we will just look at these two cases, then the two basic cases. Left, I call this left bottom to top or left to right integral. Here is a very important prototype example. You see, what we do when we integrate, we first start from the inside. We try to solve this integral. That's the same integral than we have here. It's the gifted problem. We look at that afterwards. We cannot solve the problem to find this definite integral. We will be able to solve the integral from minus infinity to infinity, but we cannot solve this integral from y to 2. So we are stuck here. This integral here is also the integral from 0 to 2 dx, and then we go from 0 to x. It is completely impossible integral we were able to do by change the order of integration. What I want to add is a Monte Carlo demonstration, because you are doing that in the project for Friday. And actually what you do is you compute the area of the Mandelbrot set with a Monte Carlo method with a computer. Now I want to do that by hand. In this case, what we have is I'm throwing balls randomly onto this box here, which has area 4. So this total area is 4. What I can do is I can just see how many times do I hit this cardioid. This cardioid makes up the main part of the Mandelbrot set. That's called the main cardioid. You can compute this cardioid area explicitly with calculus we learn here, and we get about 1. So let me just try to see how many we can shoot. So we have shot here, and I'm only taking the ones which actually have hit the target. In this case, I have shot 29 times, and I got n is equal to 29. Now let's see how many times did we hit. We have hit 12 times. Hey Siri, what is 28 over 29?
It's about 0.9655.
Not bad. I was a little bit lucky here. So you will see, even if you make thousands of experiments, you might get something a little bit off. Monte Carlo method, and you will write about this in the project. It's one of the most important things also for data analysis, that you are using random data to test things, and it's an extremely important thing also to get quantitative results. So that's Unit 15. About Unit 16, that's mainly surface integration. So when you compute the surface area of a surface, parameterized surface, you get a double integral. What you do is you actually integrate over a region which parameterizes this. So this is the parameterization R of u of v, and that's S. So what you do is you don't integrate over S, but you integrate over R, where you have control about things. One can look at polar integration as a special case when you just parameterize the plane. So that's polar coordinates. This is a parameterization of the plane with two parameters, R and theta. You can use this formula here and you get R. You can also see the R distortion factor in polar coordinates here. This is R d theta, this is d theta. So R d theta dr, that's the area of the area element in polar coordinates. It's definitely the favorite, and it has been appearing in a movie, Gifted. It's pretty cool. We can use multivariable to solve integrals which are impossible to solve in single variable calculus alone. So this is the area under this bell curve. So we will also compute the sphere surface as Archimedes has done first. Archimedes had a very clever idea. So Archimedes realized when he wanted to compute the surface area of a sphere, he can inscribe it in a cylinder. And so what he realized is that this map here, which maps from the surface of the sphere to the surface of the cylinder, is actually just area preserving. So we know if this is R, so 2 pi r times, and this whole thing is also 2r, this is 4 pi r squared. That is the surface area of a sphere. One of the beautiful results of Archimedes. And then we look at the surface of revolution, especially we look at the Gabriel's trumpet, and it's a surface which you can also then consider in the limit when this is b from 1 to b. You can look at what happens when b goes to infinity. And that's a very interesting story. Okay, I think that finishes the short version of Unit 15 and Unit 16.